Good morning to everyone. I am Irene Villa from the Institute of Physics of the Czech Academy of Science in Prague, and today I'm glad to have the possibility to present you my work, whose title is The Long-Lasting Investigation on Defects in Solids and Recent Approaches in Driving Inorganic Nanomaterials Luminescence. This investigation on the role of defects in solids has been developed mostly at the Department of Material Science at the University of Milano Bicocca, and thanks to the cooperation with the Department of Materials by ETH of Zurich, the National Inter-University Consortium of Material Science and Technology by the University of Milano Bicocca, the University Lyon 1, and the Institute of Physics in Prague. We can start the presentation with a very simple definition of luminescence. Luminescence is a phenomenon where, after the excitation by an external energy source, a material is promoted in its excited state and then release the received excitation in form of light. There can be several excitation sources, photons and high-energy sources. It is the case of photo and radioluminescence, activation by chemical mechanisms and also biological mechanisms, as it may happen in nature, called chemical and bioluminescence, respectively, activation by heat, thermoluminescence, or mechanical actions, mechanoluminescence. Nowadays, the use of luminescent materials covers a wide range of applications. Luminescent materials and phosphors are exploited, for instance, in everyday life lighting, in displays and screens of the mobile phones, as persistent sources of light in security and warning panels. Also, luminescent mechanisms are at the base of the medical devices used in diagnosis, such as in fluorescence bioimaging and in total body imaging techniques like tomography. The study of the behavior of the luminescent materials under diverse conditions and featuring different parameters, annealing, size, synthesis, as well as the attempt to understand the origin of their luminescence, are important steps for controlling the emission properties of any material and towards its specific application. There are several spectroscopic techniques that enable the investigation: optical absorption, photo and radioluminescence, thermoluminescence, and time-resolved photo and radioluminescence. Among them, I focus my attention and my investigation on the luminescent behavior under both UV visible light and ionizing radiation excitation. These techniques enable to collect hints on the nature of the luminescence in the materials by exploiting two different excitation sources, that is, two different excitation mechanisms that lead to diverse radiative recombination pathway. By considering an inorganic material, in my case I will consider a wide bandgap material, photoluminescence and radioluminescence mechanism can be, in simple words, differentiated because photoluminescence is based on an intracenter excitation, while radioluminescence is a three-step mechanism, and the radiative emission occurs only after a transport stage of the free carriers towards the emitting centers. Photoluminescence is affected mostly by the concentration of emitting centers. In turn, radioluminescence can be influenced also by other factors, like defects acting as traps, additional color centers, or non-radiative centers, especially during the transport stage. Besides the long-lasting investigation of luminescence in solids as bulk materials, there is another branch of investigation that focuses its efforts on materials at the nanoscale, that is, on nanomaterials. The two investigation lines share some common points, as the investigation of brand new nanomaterials is grounded to the knowledge of the luminescence principles in bulks. For instance, it is known that, regardless the dimensions, the presence of extrinsic or intrinsic defects in solids plays a major role in governing the luminescent behavior by introducing additional energy levels within the material forbidden gap. But nanomaterials' properties can also differ from the ones of their bulk counterparts. Chemical, mechanical, magnetic, and optical properties can be modulated in nanomaterials as their results to be dependent from the size. In my investigation, I am mostly interested in the reason why the luminescence emissions can be modulated by the size. From the previous theoretical and experimental works, it is known that the change in the electronic and the luminescence properties of nanomaterials may be related to the well-known spatial confinement, for example, in quantum dots. But also, this change in 3D materials may be due to the large surface-to-volume ratio. Indeed, size-related surface and interface rearrangements are expected, together with a change in the concentration and in the behavior of the optical active defects involved in the emission mechanism. The attraction of the scientific community in the direction of nanomaterials can be measured in terms of the adjustability of their characteristics. Composition, dimension, shape, structure, morphology, and thus the optoelectronic properties can be changed in relation to the synthesis routes, the annealing treatment, as well as the doping procedures and concentrations. The investigation on the factors influencing the nanomaterials' qualities in terms, for example, of emission colors and efficiency, timing capabilities, and radiation hardness is encouraged in the scientific community, as it is a powerful tool for the achievement of materials with high quality and customized performances. Nanomaterials are proposed for the making up of highly transparent ceramics or composites, in this case after their embedding in a polymer, thanks to the reduction of scattering, as well as to the possibility to obtain cubic phase nanoparticles suitable to be packed in ceramics. Also, nanomaterial size is comparable to the size of biological systems and elements, like proteins, some virus, DNA. Also, the nanomaterial size is much smaller than cells and bacteria. For this reason, nanoparticles can be used as a versatile agents for in vivo and in vitro techniques, from diagnosis, therapy, to robotics. As a consequence of the possibility to easily change the characteristics of nanomaterials, their use covers a large range of applications in sensing and security, in catalysis for environmental applications, for solar cells, in photonics and scintillation, in nanomedicine. In nanomaterials and nanocrystals, the luminescence properties are connected to the presence of defects in the lattice. Two types of defects are the most important for the luminescent behavior, and they act as optical active centers. intrinsic lattice defects, vacancies or interstitial atoms lying especially at the surface or at the grain boundaries of the nanoparticles, and the extrinsic dopants, rare earth or transition metal ions, for example. Nowadays, the investigation of the luminescent nanomaterials aims also to the development of new defects engineering strategies and doping routes. In it, the application of the both strategies enables to obtain nanomaterials with tunable color emissions. This is an example of hafnium oxide nanoparticles doped with europium. The blue color under near UV excitation is related to intrinsic defects. In turn, when the excitation is at higher energy, the europium emission is activated by charge transfer mechanism. Moreover, other doping strategies permit the doping with two ions. For instance, hafnium oxide can contain terbium and europium, and the energy transfer from one ion to the other occurs, giving rise to a composite luminescence spectrum and a change of the final emission colors according to the concentration of the two dopants. From 2012, supported by the cooperation between the University of Milano Bicocca and the ETH of Zurich, I have been involved in the investigation of the luminescence of hafnium oxide nanocrystals. Hafnium oxide, or hafnia, meets the interest of the scientific community because of the large quantity of its properties. For instance, hafnium oxide possesses a high dielectric constant, a high chemical and thermal stability, and can be used for electric and industrial applications, in catalysis, sensing, and for refractory application. Thanks to its mechanical resistance, hafnia finds application also as ceramic or super hard material. The reason of presenting hafnium oxide as a case of study today is due to the appropriateness of its properties also for the optical field and for scintillation. Indeed, being a wide bandgap material, hafnium oxide can be an excellent host for dopants. The high zeta number and the high density make hafnium oxide suitable in scintillation because of its ability of stopping the ionizing radiation. For example, hafnium oxide has been recently proposed in oncology as material useful to increase the effect of the traditional radiotherapy. One of the major drawbacks of hafnium oxide, that is the high melting point hindering the creation of bulks, can be surpassed by producing nanocrystals through the non-aqueous sol-gel route. Indeed, we obtain monoclinic crystals of hafnium oxide with a size of 3 nanometers in form of white powder. The very first characterization of hafnia nanocrystals were performed by XRD and TEM measurements. They both reveal that the obtained nanocrystals have a monoclinic structure and a size of a few nanometers. After annealing the samples, the dimension of the nanocrystals starts to increase up to 30 nanometers for annealing at 1000 Celsius degree. An aggregation of the nanocrystals occurs may be due to the removal of organics like benzoate group from the synthesis from the surfaces. The role of annealing can be depicted as a change in size, crystallinity degree, removal of organics, removal of non-radiative centers, and rearrangement of the surface in nanocrystals of hafnium oxide. The question now is What happens to the luminescence properties of hafnium oxide nanocrystals during the annealing? Photoluminescence and radioluminescence change as a function of the temperature. By looking at the photoluminescence under UV excitation, 4.4 electron volt or 280 nanometers, we notice that while the annealing temperature is increasing, the shape and the intensity of the photoluminescence are changing. At low temperature, nanocrystals show a spectrum composed by 4 bands at 2.1, 2.5, 2.9 and 3.6 electron volt. At high temperature, the dominant band is the one in the blue range at 2.5 electron volt, while all the others bands disappear. If we consider only the decreasing bands, the photoluminescence picture reveals that these bands may be related to surface defects, suppose oxygen vacancy related defects. Indeed, while the temperature is increasing, the size of the nanocrystal is increasing, that is, the number of surface defects responsible of the emission is reduced. If we want to understand the origin of the blue band, we must take into account the results obtained by exciting with ionizing radiation. In fact, in radioluminescence, we find the same bands as in photoluminescence, plus 2 additional ones in the UV that have been attributed to excitons. In radioluminescence, all the bands increase. Except for the blue band, the other visible bands are confirmed to be related to intrinsic defects, but under ionizing radiation, their increment is due to a different efficiency during the transport of carriers toward the emitting defect. In large nanoparticles, the transport is the most efficient, thanks to the removal of non-radiative centers that can compete during the transport stage of radioluminescence mechanism. For this reason, the radioluminescence increase is expected while the nanocrystal size and the annealing temperature rise up. The photoluminescence and the radioluminescence increase of the blue band reveal that these bands can have a different origin, and especially it can be related to the presence of impurities in the lattice that can be activated during the annealing temperature increase. Among impurities, titanium is the most probable in hafnium oxide lattice. So, by now we know that besides the intrinsic bands, there can be a blue band associated to an accidental titanium impurity in the lattice, whose intensity is dominant in the spectra of samples treated at high temperature. Aiming at going deeply on the origin of the intense blue band of hafnium oxide, we studied the photoluminescence emission and photoluminescence excitation spectra of one sample of hafnia treated at low temperature, another sample treated at high temperature, and a third sample of hafnia doped with titanium and annealed at high temperature. The comparison of the excitation, the emission spectra, shows that titanium impurity is optically active only in the largest nanocrystals after the annealing and under high energy excitation. On the contrary, by exciting in the near UV range, close to 350 nanometer, we can observe the intrinsic defect emission of hafnia nanocrystal. Time-resolved photoluminescence confirms the activation of titanium only in the largest nanocrystals under high energy excitation and with a lifetime of a few microseconds. Importantly, the results reveal the presence of an intrinsic blue band with a time decay in the nanosecond range in the smallest nanoparticle. All the explained results are displaying the possibility to control the emission properties of hafnium nanocrystals by simply selecting the thermal treatment that influences the surface defect arrangement. In particular, hafnia intrinsic defects can be efficiently excited by near UV light, but the color of the final output varies according to the surface-to-volume ratio, the size, the porosity, and the crystalline degree of the nanocrystal. While annealing the hafnia nanocrystals, we assist to a change of the spectral features. In particular, nanocrystals annealed at 600 Celsius degree under near UV display a white emission. The white emission results from the contribution of the emission at 2.2 electron volt that at 600 Celsius degree is maximum, and it might be due to the incorporation of contaminants or the elimination of passivation on some defects. The results in this field may be a starting point for the design of optimized defect engineering strategies and the development of dopant-free white phosphors based on hafnia nanocrystals. The intrinsic luminescence of the smallest hafnium oxide nanocrystals treated at low temperature was characterized by time-resolved photoluminescence and scintillation decay measurement. The small nanocrystal show the intrinsic blue emission band both under light and under X-ray irradiation with the same time decay. Indeed, the fit analysis of the two decays reveal the presence of a multi-exponential decay. Among the components, the fastest one is of 5 nanoseconds. Despite the low intensity of the blue intrinsic emission, we can consider hafnia for potential uses in scintillation detectors. For further optimization of the hafnia timing response and light yield can be pursued through the optimization of the synthesis and the post-synthesis treatment. In parallel to the exploration of the intrinsic luminescence of hafnium oxide and the investigation of the strategies to optimize the emission output, we should consider the way to exploit the titanium-related blue luminescence in hafnia. Indeed, even when titanium is present in hafnia lattice as impurity, the blue emission related to it displays a huge increase as a function of the temperature and the nanoparticle size. For samples annealed at 1000 Celsius degrees, the intensity of the radioluminescence emission due to titanium is close to the one of BGO standard. As I described at the beginning of my presentation, the control of the luminescence properties of inorganic nanoparticles by adding extrinsic dopants is a very well-known strategy. The development of new doping strategies stays in a one-to-one connection with the understanding of the physical phenomena occurring between the dopants and the host lattice and the design of novel efficient luminescent materials and scintillators. The most used highly emitting dopants are rare earth, but recently also titanium transition metal ion has been proposed for scintillation, being responsible of an increase in the light yield of inorganic hosts like zirconium oxide and hafnate crystals. However, the luminescence property of titanium in a wide-bandgap host still represent an active topic of investigation. Hafnium oxide nanocrystals are excellent hosts for titanium, since these ions can be naturally incorporated in the lattice, and it gives rise to an intense luminescence even at very low concentration. Here I present the results obtained for hafnia doped with titanium. Hafnium nanocrystals have been prepared and doped with increasing concentration of titanium from 0.003% up to 10%, and then a thermal treatment up to 1000 Celsius degrees has been performed. TEM and XRD measurements reveal that the monoclinic hafnium nanocrystals have a size of 3 to 8 nanometers for annealing from room temperature to 500 Celsius degrees. Titanium concentration does not influence the size nor the monoclinic structure. When temperature increases, the growth of one order of magnitude of the crystal size occurs, together with the agglomeration of the crystals, due to the decomposition of organics from the crystal surface. However, high-temperature annealed samples doped with contents of titanium higher than 1% show a decrease of the diameter. The picture resulting from the radioluminescence spectra of hafnium oxide doped with titanium is complex, but for one more time it explains clearly the strong importance of good doping strategy and good annealing routes for the control of the light output of nanomaterials. If we consider the untreated hafnia, we can notice that the luminescence features are similar to the ones of undoped hafnia. This means that when the sample is not treated, the intrinsic defects play the major role in driving the luminescence behavior. This fact is also supported by the XPS data, as they reveal the presence of both titanium 3+ and titanium 4+ in the lattice. Since the presence of trivalent dopant ion involves a charge compensation in hafnium oxide, defects like vacancies are created, and so, in the smallest nanoparticles, the intrinsic defects are efficient luminescence centers. For intermediate temperature close to 500 Celsius degrees, the spectra are peaked at 2.5 electron volt for low titanium concentration, and then they are shifted to lower energy. Despite the fact that this behavior is still unclear, we can consider that at this temperature, where a partial surface rearrangement starts, a competition between the intrinsic center and the titanium center is responsible for the change of the luminescence features. After high-temperature treatment, radioluminescence spectra are dominated by the blue band, and the XPS spectrum exhibits only the titanium 4+ component. This results from the oxidation of titanium 3+ to titanium 4+ during the calcination process. Titanium 4+ is not expected to be luminescent, but a charge transfer transition from titanium in connection with surrounding oxygen is proposed as origin of the 2.5 band. The most important result obtained in the investigation of the luminescence properties of titanium-doped hafnium oxide under X-ray excitation is the achievement of highly luminescent nanocrystals. In fact, the strategy of doping the nanocrystals with titanium has been successful. Then, the following thermal treatment procedures are able to activate the titanium centers, and the final intensity of East blue emission after annealing at 1000 Celsius degrees is equal or even higher than the BGO intensity for content up to 1 molar %. Despite the very high intensity in the blue region, the long scintillation decay time is not suitable for the use in fast timing techniques. Nevertheless, new medical treatments require the use of scintillating materials without implying strictly requirements in timing performances. For example, the blue titanium radioluminescence emission can activate cancer-killing agents like oxygen photosensitizer for the photodynamic therapy activated by X-rays. Another important case of study regards the zinc oxide nanoparticles. Especially in this presentation, I will focus the attention on zinc oxide nanoparticles on silica support. In general, zinc oxide is a material with properties suitable in a very large range of applications. It is transparent in the near UV range and shows luminescence features with both excitonic origin and intrinsic defects-related nature. Today, zinc oxide is used in optoelectronics, in photonics, in sensing, in the scintillation field, as well as in rubber industry, nanomedicine, and cosmetics. A detailed description of the zinc oxide properties is proposed in the oral contribution of Roberta Crapanzano from the University of Milano Bicocca. One of the major problems of zinc oxide is its involvement in the production of harmful persistent radicals in the environment. Indeed, environmentally persistent free radicals enclosed in fine, ultrafine particulate matters can survive in the atmospheres for months, and they are responsible for human pulmonary diseases and also for DNA damage in the human body. The comprehension of the generation of these very stable radicals through the interaction of aromatic molecules and metal oxides is still under debate. Especially in the case of zinc oxide nanoparticles and phenols as aromatic molecules, it is known that the generated radicals are the most stable in the atmospheres, up to 73 days. Here, we consider zinc oxide nanoparticles on silica supports with different shapes. The investigation of the defectiveness of zinc oxide nanoparticles arising from the different structural, morphological, and surface features must be considered in relation to their surface reactivity in the formation of persistent radicals. Zinc oxide nanoparticles with an average size of 5 nanometers are anchored on silica supports with both spherical and rod-like shape. These systems simulate the particulate matter. Photoluminescence and electron spin resonance measurements have been conducted aiming at the understanding of the role of the zinc oxide intrinsic defectiveness for the stabilization of the phenol radical. As it will be explained by Roberta Crapanzano, zinc oxide is known to be rich in intrinsic defects, like oxygen and zinc vacancies or interstitials. These defects are responsible for the luminescence behavior of zinc oxide. Moreover, some defects give rise to ESR species, like singly ionized zinc and oxygen vacancies, as well as oxygen ion. The choice of the synthesis and growth parameters influences the morphology and the structure of the zinc oxide nanoparticles attached on the silica supports, and thus the intrinsic defectiveness of the samples. Photoluminescence and photoluminescence excitation measurements reveal that zinc oxide grown on spherical support can be excited with energy above the band gap, giving rise to a green luminescence at 2.2 electron volt. The origin of this band is under debate, but it may be due to surface defects. The same green band is seen also in the zinc oxide grown on rod-like silica supports, but with a weaker intensity. The weaker intensity may be due to the presence of quenching channels in these samples and to a lower concentration of surface defects. Indeed, the zinc oxide nanoparticles attached on rod-like silica are characterized by a higher crystallinity degree. Moreover, zinc oxide on rod-like surface can be excited with energy below the band gap at 3.1 electron volt, and the following emission is peaked in the blue range at 2.6 electron volt. Silica support signal under UV is negligible. These results indicate that morphological factors in terms of size, growth parameters, and interfaces are strongly influencing the type and the concentration of surface defects of the zinc oxide nanoparticle, and as a consequence, their optical properties. The presence of paramagnetic defects has been checked through ESR measurements. Moreover, the typical process at the base of the formation of environmentally persistent free radicals has been simulated through the exposition of zinc oxide nanoparticle to phenol vapor. Briefly, the obtained results prove the presence of different paramagnetic species due to defects lying in proximity to the surface of the zinc oxide nanoparticles, whose relative contribution in the ESR spectrum is maximum for zinc oxide on rod-like silica before and also after the interaction with phenol. On the contrary, ESR spectrum of zinc oxide on spherical silica is collected only after the exposition of vapor, revealing the presence of a weak signal attributed to the phenol radicals. These results prove that the presence of different surface defects in zinc oxide can either hinder or create the environmentally persistent free radicals on metal oxide surfaces. For my presentation, I have chosen hafnium oxide and zinc oxide as representative nanomaterials due to their outstanding qualities. The focus of my presentation has been the description of the different factors that enable to govern the luminescence properties of nanomaterials. From the choice of the synthesis, the use of doping strategy to the annealing treatments, all these procedures allow to control the nanomaterial size as well as the type and the concentration of defects that can either switch on or quench the luminescence as demonstrated for the case of hafnium, or also they can affect the surface chemical reactivity as in zinc oxide nanoparticles. Moreover, I have shown that the different effect of the optical light and the ionizing radiation excitation must be taken into account while investigating nanomaterials. From the point of view of the application, the knowledge of the physical chemical factors influencing the luminescence at the nanoscale, together with the development of targeted defects engineering and doping strategies, are mandatory toward the design of cutting-edge and highly performant nanomaterials.